This is SpaceTime Series 21, Episode 70, for broadcast on the 5th of September 2018. Coming up on SpaceTime, Earth's magnetic field reversals could happen faster than thought. The New Horizons spacecraft spots Ultima Thule, its next target. And a leak venting atmosphere into space sparks an emergency aboard the International Space Station. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
A new study suggests that Earth's geomagnetic field polarity reversals could occur over timescales of just 2 centuries, much faster than previously thought. The findings, reported in the Proceedings of the National Academy of Sciences, are based on studies of limestone stalagmites in a Chinese cave. Earth's magnetic poles flip their polarity roughly every 280,000 years. Although, to be honest, the last occurred around 780,000 years ago, and that suggests the planet's well overdue for the next. In the last 83 million years, there have been 183 pole reversals. And previous studies based on rock solidification evidence suggest that these polarity reversals could take thousands of years. But this new study, based on paleomagnetic records between 107,000 and 91,000 years ago, has narrowed this down to just a couple of centuries. Scientists were able to develop the new chronological timescale using a more accurate magnetic analysis, which provided radiometric dating of a 1 metre high, 8 centimetre wide, candle-shaped brown and yellow stalagmite discovered in a cave in southwestern China. One of the study's authors, Professor Andrew Roberts from the Australian National University, says the stalagmite data shows that magnetic field strength decreased by about 90% when the field reversal occurred, making the Earth far more vulnerable to the sun's radiation. The Earth's magnetic field provides a shield from the direct impact of solar radiation. And even with Earth's strong magnetic field today, the planet is still susceptible to solar storms from the sun, which threaten astronauts in space, damage satellites by overloading circuits, black out communications and navigation systems, and destroy terrestrial power grids, cutting electricity supplies to wide areas. A similar event in the future will increase exposure to the sun's radiation. And because of today's technological society, that would cause trillions of dollars in damage to communications and power systems. Roberts says a magnetic field reversal would have far greater impact than solar storms.
So stalagmites are amazing things. You've been into a cave, no doubt, and you've looked up and you see drip water coming down from tubes at the top of the cave. Those are called stalactites, and the drip water drips onto the bottom of the cave. That water carries minerals that precipitate out of the solution to form a stalagmite. And that stalagmite is what we sampled for our study, and it's about 1 meter long. And we took samples right down the middle of it. And the amazing thing about the mineral content of the drip water inside these caves, I mean, if you walk through a cave system, you get dripped on all the time. And this drip water carries little soil particles from the soils above. And those soil particles, some of which are magnetic, get aligned with the Earth's magnetic field as they settle onto the stalagmite below. And then they get cemented in place as the calcium carbonate precipitates out of that solution to grow the stalagmite. And so what you get is this amazing record of the Earth's magnetic field within these stalagmites. And you can also date those individual layers from measuring with super high resolution mass spectrometers, the uranium and the thorium content. And you can measure how much of the original uranium has decayed to form the daughter thorium. And by taking the ratio, you can get the age. So from a simple cave deposit, you can get a remarkable record of how the Earth's magnetic field has changed back in time.
More than just limestone.
More than just limestone. It's an amazing thing. Now, think about it. Limestone is like, it's not chalk in this case, but some limestones are chalk. And so it's a pretty clean material. It's not very magnetic at all. So you need a super duper magnetometer to measure these things, which we've used. And the sensitivity of the uranium thorium dating is also extraordinary. So it's not easy to get records of this type. It's taken about 10 years of work to find one of these stalagmite deposits that's giving us really measurable stuff. But now we're on a roll. We're starting to get more of these things because we know what we're looking for. So it's really spectacular what you can do with these recorders.